We will start. Ladies and gentlemen, this is my great pleasure to introduce you to this new session and also to the recipient, Chigomizio Ngwira. The new generation of scientists is a new union session dedicated to the work of young and early career scientists, including the Science for Solutions Award recipients. This session is expected to evolve in the coming years and will gather other young AGU medal recipients, but we will start this year by the younger generation of scientists. The Science for Solutions Award, established in 2012 by the generosity of Peter Schlosser, past president of AGU's Ocean Sciences section and professor at Columbia University and Lamont Doherty Earth Observatory, is given annually to one student or postdoctoral scientist in recognition for, quote, significant contribution in the application and use of the Earth and space sciences to solve societal problems. This award includes $1,000 monetary prize towards advancing his Earth studies or projects, engraved crystal award, recognition in EOS, invitation to present a lecture at the AGU fall meeting during the award presentation year, so this is the case, recognition at the AGU fall meeting during the award presentation year, and not but the least, the 2 complimentary tickets to the honor banquet of the AGU fall meeting during the award presentation years. Ladies and gentlemen, please join me to welcome the recipient of the 2014 Science for Solution Award, Chigomizio Ngwira, from NASA Goddard Space Flight Center, Greenbelt, who will give the presentation entitled Extreme Space Weather Studies Addressing Societal Needs. Stay with you.
Thank you. Thank you very much. It's an honor to receive this award. And so my presentation this afternoon is basically on extreme space weather and how important it is in solving societal problems. But I thought before I go into my presentation, maybe I'll just say a few words about myself. And so I started my undergraduate studies in physics at the University of Zambia in Zambia. And it was after I completed my bachelor's degree that I moved on to South Africa to pursue postgraduate studies. And so that's when I got introduced to the studies on space science, and in particular geomagnetically induced current. So I did a master's degree based on geomagnetically induced current. I worked with Dr. Antti Pukkanen, who later became my postdoc advisor. And so after completing my master's, I did a PhD at the University of Rhodes in South Africa, and then I moved to the US to pursue a career as a postdoc in 2012. So that's the journey that has brought me here, and I think I'm very privileged to have the opportunity to present to you about some of this work that I've been doing in my postdoc. Right, next slide. I have that. Okay. Oh, okay. Oops. What have I done? Okay. So this is going to be the outline of my talk. I'll introduce what space weather is and some of the effects of space weather. And then I'll move on to talk about geomagnetically induced currents, which are the end effect of space weather. And then why is it that we care about space weather and geomagnetically induced current? And then I'll present the objectives of our research and how we're using MHD models to be able to achieve these objectives. And I'll give a brief highlights of some of the research that I've been doing on extreme space weather modeling before I do a summary of my whole talk. Okay, so this is a schematic of the space weather lab, so to say. And we have the sun on one side, and we have the Earth, which is shielded by its magnetic field, forming this region called the magnetosphere, where the Earth's magnetic field is dominant. And so we have the sun and the propagation of solar wind from the sun, which contains particles and the magnetic field of the sun. And it's the interaction of the magnetic field, the particles, and the magnetic field of the Earth that we have these storms within the Earth system that give rise to the phenomena of geomagnetically induced current. And so the term space weather itself just means conditions on the sun and in the solar wind, which is propagated from the sun to the Earth. And we're also talking of conditions in the magnetosphere, the ionosphere, which is the region inside the magnetosphere, about 100 kilometers above the Earth's surface, and how these influence space-based or ground-based technological systems. Now, they have excluded here also something which has to do with human life, which is astronauts in space can also be impacted by space weather. Now, the sun, of course, is the primary driver of space weather, and of most concern to us is when we have these solar eruptions, coronal mass ejections that propagate from the sun to the Earth, that we have these induced currents at a higher elevated level. And so the interaction of the sun magnetic field and the Earth magnetic field then gives rise to these geomagnetic storms. So this is a picture that shows various effects of space weather. And I've talked about humans in space being impacted by high radiation particles. You also have, if you have a lot of density in the ionosphere or magnetosphere, which will cause drag on satellite. You have the ionosphere, which is a medium that is used mainly for propagation of radio waves, that during geomagnetic storms, the conditions in the ionosphere can change to an extent where you have disruption of satellite signals that are passing through the ionosphere. And this will interrupt GPS signals or other high-frequency radio signals that are used to propagate through the ionosphere. Also, charging of satellite is another effect. But of concern to us and our studies is this geomagnetically induced current, which can flow in technological systems on the ground. You're talking of oil and gas pipelines. You're talking of communication cables over the seas. And you're also talking of electricity grids, which is, when you look at the technological systems, is the most critical because of the wide variety of application for electricity. And so the phenomenon of geomagnetically induced current itself, as I've said, begins with the sun on one side, the propagation of the solar wind, interaction of this solar wind with the Earth magnetosphere, that then through these current systems that are in the magnetosphere and ionosphere causes these disruptions, and the rapid fluctuation of these currents then induce an electric field on the ground, which leads to the flow of geomagnetically induced current on any Earth conducting system, long transmission lines. And it's because of this rate of change of the magnetic fields by Faraday's law of induction that gives rise to the geomagnetically induced currents. So in modeling geomagnetically induced currents, typically we apply a two-step process. And in the first step, we look at the modeling of the geoelectric field on the ground. And modeling of the geoelectric field on the ground is where you apply the physics to the whole problem. And so what we're doing is we're using current, we're trying to understand the currents that flow in the magnetosphere and the ionosphere in combination with the ground conductivity in order to derive what is the electric field. And so you have the magnetic field on one side and you have the conductivity, which are then used to model what the geoelectric fields. And then the second process after you have derived the electric field is now the application of this electric field to solving equations that are then used to determine the flow of GIC on your power transmission network. And so to do this, we use the electric field. The A and B parameters are typically, I would say, specific to any power transmission network node. So it will vary from one node to the other node. And when I say node, I mean typically a power transmission substation where you have these huge power transformers that then the GIC can flow through. Okay, now I talked so much about geomagnetically induced current, but what does it look like in terms of the scientific data? And so this is scientific data for a storm that happened on October 29 to 31 in 2003. And the GIC itself, the current, is here presented in this bottom panel. And then the rate of change of the magnetic field, which I say is responsible for the electric field on the ground, is depicted here. So you have two components. You have one component in the north-south direction, and the other component is the east-west direction. So we use these two components to derive the geomagnetically induced current. So this is for a study that we did in 2009, and this is a representative of GIC flow in a transmission line in South Africa. This is the quiet time, and then when the storm starts, this is at that period where you see the geomagnetically induced current levels suddenly change from being quiet and to these rapid fluctuations. And it's typically during those intervals that we are worried about the effects on the power transmission networks. Okay, so there are really two reasons why we care about geomagnetically induced current. And from my perspective, the first and most important is about the science. We want to understand the physics concerning geomagnetically induced current, how they are produced, and the characteristics of the currents that lead to the geomagnetically induced current. And the other reason, of course, is in terms of the effect on the power transmission network. And so I'll talk about the two, but first I'll start with the physics. And so to understand this geomagnetically induced current, we're looking at a very long chain of events, of course, starting from the sun to the ground, and you have different systems that contribute to the currents on the ground. And you have to understand the physics from the sun to the mud, so we say. And so to do that, you need to understand the ground conductivity, the geology of where your power transmission network is, because the geology contributes to the level of geoelectric field on the ground. You have to understand the current systems within the Earth magnetosphere-ionosphere in order to model the ground geoelectric fields. You also have to understand the interaction of the solar wind, which is from the sun, and how it interacts with the Earth magnetosphere. But then you also have to understand the propagation of the solar wind, or its coronal mass ejection, how it's propagated from the sun to the Earth. You have to understand the properties of these CME as they propagate. And you also have to understand the source of these coronal mass ejections, which is the sun. So we have to understand something about where these coronal mass ejections are coming from. And so this whole long chain of events is what helps us in building more accurate forecasting models that are helpful in terms of mitigating the effects of geomagnetically induced currents on power transmission networks. And so when we get down into the physics, there are various regions within the Earth magnetosphere, on the Earth globe, where the geomagnetically induced currents will impact. You have regions we call the high latitudes, which are typically confined to the polar regions. You have regions on the equatorial regions. you have zones on the equatorial regions which have a different current system impacting them from what is happening in the polar regions. And in between the two, we have what is known as the mid-latitudes. And so to be able to derive or model the geoelectric fields on the ground, you have to first of all know where you are so that you understand the current systems that contribute to the electric field on the ground. Now, if we typically look at the high latitude regions, of course, which is the region that has the largest geomagnetically induced current levels during a storm, there are different drivers of these geoelectric fields. And so this was a study done by Vujanin. This is in Finland for a station at Matsala, and they looked at storms between 1998 to 2005. And what they came up with is the times that the geomagnetically induced currents exceed that level of 2.5 amps. And so they were able to determine that for a high latitude station, typically substorms are the main drivers of the large GICs. Now, substorm is this sudden release of energy within the magnetosphere on the tail side. And this release of energy is then transmitted or mapped onto the ground at the high latitudes in the Aurora region. And so this is very intense currents in the high latitude, which then drive these high GIC levels. They also found that apart from that, pulsations also contribute to the levels of GIC, high levels of GIC in the high latitude. And pulsation means the time that the solar wind hits the Earth, these waves which are transmitted from the day side where the solar wind hits the Earth into the inner side of the magnetosphere can also drive these currents. And then if you move from the high latitudes, you come down a bit into the mid-latitudes, which is where most of the continental US falls. You find that the current drivers in here are also different. And this was a study done by Pukanin in 2010. And they looked at various storms. And what they found that in the mid-latitudes, mainly during the early phase of the storm, there was high currents. And also during sudden commencement is at the time that the solar wind hits the Earth. And at that point, there's intensification of currents on the day side, which then contribute to this sudden commencement. So they also found that coronal mass ejections were the most significant were the most significant driver of GIC at the mid-latitudes and the high latitudes. And then recently, in 2012, we did a study that looked at the most significant storms that happened between 1989 to 2005. And so during that period, we were able to pick 12 storms. And for these storms, we were trying to see what the geoelectric field distribution would be on a global scale. And so what you see in this picture is that this is the electric field, maximum electric field for a given storm. And so each dot represents a particular station on the ground. And so we're looking at the whole globe for which we had data, for stations where we had data. And typically, this is what we find. So these are geomagnetic latitudes, and they're moving from the high latitudes where the currents are higher, of course, into the mid-latitudes, and then you have the equatorial regions. And so we found that there was this region, as you're moving from the high latitudes into the mid-latitudes, where the electric field sort of just drops off by about an order of magnitude. And this region is not static, but it's a dynamic region, and it will move according to the level of storm which you have. So for very large storms, this region can extend further than 50 degrees geomagnetic latitudes. And then something that was sort of new, but not really new, but had been noticed before by a study by Pukanin, but which was confirmed in our studies, and we were able to explain what was the mechanism that was driving this, was this influence of the equatorial electrojet on the geoelectric field. Because typically in the old days, it was thought that GICs would only impact mainly power transmission lines in the high latitudes. But then we have had failures of transformer in mid-latitude stations, specifically in South Africa. So that's a mid-latitude, but it was strange that we now found that actually when you're at the equatorial region, you should be concerned because the electric fields there during certain storms are actually much larger than what is experienced in the mid-latitudes. And so this came out of this study, and we were able to establish that it was because of these penetrating electric fields at the time of the sudden commencement that this electric field suddenly just penetrated from high latitudes to the low latitudes that created this enhancement of electric field, which is now a concern for most of the power transmissions that are developing in the equatorial regions. For instance, Brazil and China are in this region, so their networks can be impacted by such kind of current. All right, so the second reason why we really care about geomagnetically induced current, and which has severe societal consequences, is on the technology side, which is the impact of these currents on the power transmission transformers themselves. And so typically these high voltage transmission power transmission transformers are operating on an AC current, which means they're operating at a frequency of about 60 hertz for America, and it's about 50 hertz for other countries like the UK or Europe. Now, GICs are a low frequency current, so meaning they're close to a DC current. And it's when the GICs flow through the power transmission transformers that they give rise to this phenomenon called half-cycle saturation. Now, what happens is that when the transformer saturates, it is forced to operate outside of the design limit. And that is of concern because eventually the transformer can be damaged because of these GICs. This is an example of a damaged transformer from South Africa, and this was for the Halloween storm of October 2003. Damage to transformer is not the only problem, but blackouts. This was a picture taken after the same Halloween storm that crippled the network, that damaged transformers in South Africa, but this is in Sweden, in the city of Malmo. And so there was a blackout because the transformers were forced into saturation, and eventually the transmission network just collapsed, and so this led to a blackout. But then when you talk of GICs, the most famous example of a storm that people always refer to in the field is the March 1989 storm. Now, this storm caused the collapse of the Hydro-Quebec network in Canada. So the entire network of the province of Hydro-Quebec collapsed after experiencing severe storm conditions. And this led to, I think, about 6 million people going without electricity for about 9 hours. Not only that, the consequence for the power transmission line for losing that period of 9 hours was in the millions of dollars in terms of lost revenue. And so that is typically why we're so concerned with geomagnetically induced currents. It's because of these such effects. And because of such effects, we are paying so much attention to understanding what really is driving the geomagnetically induced currents, what are the characteristics of the electric fields on the ground. And so there have been a lot of reports or studies that have been done to look at the impact of geomagnetically induced currents on the bulk power transmission network. So these are examples of these studies. And recently, the Federal Energy Regulation Commission instituted an order on May of 2013 requiring all power transmission operators to institute some kind of standard for the mitigation of geomagnetically induced currents. As you can imagine, this is an order on everyone to do something, so there is currently a lot of interest in understanding extreme space weather in terms of how it can affect the power transmission networks. So our work is helping in terms of defining the extremes of space weather and using this information for power transmission people to assess what could be the impact of such kind of conditions on their specific transmission grids. Okay, I have some water, sorry. So this is another example of a study that has been done. Yeah. And now, I've talked of this order, which compels all power transmission operators to institute some standards against the geomagnetically induced current. And what we're really doing is, from the space physical and geophysical side, to define these extreme storms and analysis, and then use these for the engineering analysis on the power transmission networks. And the question about these extreme kinds of GICs is not just of interest it's of interest, of course, from a basic science point, but it also challenges our understanding, because for most of the significant severe storms, we don't really have that many, and we don't have that much data to work with. And so we have to define these scenarios that will help us in order to understand the extremes. So here's an example of just some of the severe storms that we know of. And if you look, these are the day, the month, the year, and in here we have the maximum DST. Now, DST is a measure of the amount of energy that for a specific storm, when we talk of the energy on the ground. And you can see these severe storms. I've highlighted the October 2003 storm, the one that caused problems in South Africa and caused problems in Malmö, Sweden. I've also highlighted the March 89 storm, which caused the collapse of Hydro-Quebec network in Canada. But then there is this one storm, which is popularly known as the Carrington storm, which occurred in 1859. Of course, during that time, we didn't have so much of data to work with for this storm. So the data is scanty, and to my knowledge, there is only one complete set of data that you can really look at and see how the storm progressed from the beginning to the end. Most of the other measurements in terms of the magnetic field that were taken for this storm went out of scale. And so the Carrington event is known to be the largest ever recorded storm in our history. And so if really you're going to define extreme space weather, then you must be working with something in that scale. And you can see, if you compare the March 89 storm, of course there's questions about the extreme that the Carrington storm went. Other studies say it could have been minus 1,600. Others say it could have been minus 850 nanoteslas. But in whichever way you define it, it means the Carrington storm is probably about 1.4 times larger than what this March 89 storm could have been. And so if we look at extreme space weather, then we must be looking at something larger than the 89 storm on scale. And so that is what our research has been on. We've been trying to define extreme space weather, moving from something that we've experienced in the recent times and trying to work our way towards what we think was the largest ever storm that we've observed. And then you can click the movie. You can click on the movie. Click inside, yep. Okay. So here, what I have is just a representation of the global, in terms of the electric fields. So this is a global picture, and you can see this is quiet times, and you can see very small dots appearing here and there. And then at the time that the storm itself begins, you can see the variations for different stations. There's all this craziness going on. But this is what we have to work with. And in order to be able to accurately model the geomagnetically induced currents, you must understand the dynamics of the electric fields on the ground. And it's not an easy process. So there's a lot that has to be put in to do that. And so in order to do that, then we must be able to understand the physics. We must capture what is in the near-Earth space environment, because the environment itself is highly complex. There's so many current systems that have to be taken into consideration in order to produce this accurate modeling of the electric fields on the ground. So this is a representation of the magnetosphere and the various current systems that exist within this whole near-space environment. So to do that, then, our objectives really is to try and define this extreme space weather, which is, of course, low probability, but high impact. And to be able to do this, we've turned to these state-of-the-art science models, and these are available at the Community Coordinated Modeling Center, hosted at the NASA Goddard Space Flight Center in Greenbelt, Maryland. And so what we're trying to do is to use these first principle-based models to understand the response of the magnetosphere and ionosphere to various kinds of worst-case sort of scenarios for GICs. And so our team is playing a very critical role in trying to mitigate these effects on the power grid by understanding what these geomagnetic hazards really are and trying to characterize these hazards. So a few words about the CCMC. So CCMC is a multi-agency organization formed by a multi-agency. And the specific task for the CCMC is to support research in terms of development of the next generation space physics model, and also to help the transition of these models to operations. And this is part of the dedicated team of staff that is at CCMC. We have a group of computer science people, and we also have people that are working on the science side. But just in case you haven't seen me, I'm there. All right, so there are a lot of models that are housed at the CCMC. And really, we're talking of from the sun up to the ground. And so this is a long chain of models that can be used. And so there are various models that look at the sun, look at the inner heliosphere, and then you have global magnetosphere models. You have models that work for the inside, the ionosphere, and so it's a lot of models. But for our purpose, we've been using this space weather modeling framework, which is being developed at the University of Michigan. And this is a physics-based model, magnetohydrodynamics. And what we've been doing is to combine various components of the space weather modeling framework. We have a global magnetosphere model, we have an inner magnetosphere model, and an ionospheric electrodynamic model. And by combining or coupling these models together then helps us to be able to get the quantities in terms of magnetosphere currents, ionosphere currents, and these field-aligned currents, which then determine the geomagnetic field on the ground. It's the magnetic field perturbations that we use for modeling the electric fields. And so this is just how these systems are coupled, these models are coupled to be able to get the perturbations of the magnetic field. And so with this model, the good thing is that now there's an inclusion of these magnetosphere currents, which means that in terms of GIC modeling, GIC forecasting, it's not only restricted to the high latitudes, but we can now model the geomagnetic field at any location on the globe, which means we can do it for any place. And so that's the biggest advantage of using these physics-based models. Here's an example of some of the work that we've been doing in the recent times, and this is just a depiction of the response of the magnetosphere to extreme forcing of the solar wind. And we'll be able to see these are field lines depicting the magnetic field of the Earth, and there's various things happening in this environment. So the white line defines the region where you have open magnetic field lines and closed magnetic field lines. Now, open magnetic field lines means the magnetic field line starts at one point here and comes back at the other point here. And that's closed. And the open is these magnetic field lines that then you don't see it coming back down here because it continuously goes into space on the other side. So this is the X component and the Y component, and depicting this equatorial plane view of the magnetosphere. The night side, and this is the day side. So the sun is on this side so the solar wind is coming in from that direction and impacting the Earth. And what we see is that the magnetosphere, the magnetopause at the front here, is significantly pushed inward. And this is beyond where the geosynchronous orbit is. That's where the orbit where most of the satellites are sitting. So if you were to have such an extreme kind of storm, means that all your satellites within the geosynchronous orbit would actually be exposed to the solar wind, direct solar wind influence. And here we're just trying to look at the current systems, how the current responds. This is for a quiet time, and this is for a time when the solar wind is very extreme. And what you see is these field-aligned currents. So you have the blue and the red. So you have these currents inside is called the region 1 field-aligned current, and on the outer side is the region 2 current. And so here they are well defined, but when you come to the extreme kind of forcing, you see that the currents are not really well defined. You can see clearly the region 1 currents, but in terms of region 2, everything seems to have broken down. And then the other thing we also note from this figure is that this white line, which is just defining the polar cap region, is significantly pushed to latitudes where we do not expect it to be. And this is of importance for airlines because they fly these airplanes across the poles to sort of cut down on time. But then, during such a storm, you expect that the high energy, which is really of concern when you're flying through the high latitudes, can be in a region where you don't really expect it to be. And though it's only by looking at the science side that you can really be able to define and understand how space weather will impact you in that way. And so we're able to define that this region can actually be moved, and this would be of interest for airlines. Of course, we've tried to understand exactly what could be driving these complex systems, current systems, during very extreme kind of storms. And we have looked at various studies which have also looked at these complicated kind of current systems developing for severe storms that we have observed. And here are a few studies. And this is Bihara. They studied the ring current and how the magnetosphere and ionosphere coupling changed during this storm in 2003, and they were actually able to find that this region 2 current, which is driven by pressure gradients in the tail region. So this picture shows the pressure during, this is a cut, and showing the pressure, and you can see there's this intense pressure on the night side, and so we believe this intense pressure drives these region 2 currents. And so what we found was that for this storm, this pressure was actually very, very large, larger than anything that has been seen from observed storms. And so this is exactly what these guys found, that they also showed that the region 2 currents could be complicated when you go into severe kind of storms. And another group also did the same kind of study, but looking at another storm. And what they found was that actually the small scale, there was evidence of small scale structures, which means there was sort of a breakdown of the whole current systems. You have these smaller current systems existing within the same region. And so these are some of the studies that we're trying to help to really understand extreme space weather, because some of these studies have never been done on this scale. So it's important for us to be able to understand if we go extreme, then what would be the reaction in the magnetosphere and ionosphere? Is it something we have seen before? If not, then we need to explain what is really causing this kind of changes in the magnetosphere and ionosphere system. And then, of course, because the extreme kind of events we've been doing are outside of what has been observed, and so we have to find a way of really defining if the models are reproducing something which is physical and not garbage. And so we have to do some kind of validation process in terms of the modeling. And what we did with our extreme events is that we looked at the cross-polar cap potentials. So this is the potentials in the high latitude regions. And this one, the black line, is for Cisco Hill. This is a well-known sort of model that they use for driving the cross-polar cap potentials. And then this is, the blue is what we're getting from the MHD solution, which is the physics-based models that we're using. And so there's a well-known fact that the cross-polar cap potential saturates as the electric fields. The interplanetary electric field is the electric field that is contained within the solar wind. So that's why it's interplanetary electric field. And so as the interplanetary electric field increases, then the polar cap potential at some point will saturate. And what we found from using these models is that actually the polar cap potentials do saturate. But then if you're going extreme, then it means the saturation also occurs at very elevated levels. And so this is above the levels that have been previously observed. I think the highest saturation point I've seen from literature is around 500 kilovolts. And so this is about 4 times that much. And so these are some of the things that we need to look at and understand how they can change with extreme space weather conditions. And then we looked at the electric field response for these extreme storms. And what we have, I'll start with the right side. This is similar to the other picture I showed, where you have the electric fields and the geomagnetic latitudes. Now, the top panel is for what we term as a Carrington type of event. So we're trying to simulate that, the biggest of storms that has been observed. So this is what you would get in terms of electric field. And then the bottom panel is for the Halloween storm, which is the 2003 storm, the October 2003 storm. And you can see the two. In terms of the structure, this looks very similar. There's a similar pattern. And for this one, we have what we did with simulation, which is the blue, and the red dot represents the actual observations. So we're using data that is from the observations. And we are comparing with the modeled geomagnetic perturbations, which are used to derive the electric field. And you can see that there's a very good agreement in terms of what the physics model is doing and the actual observation. So we were very happy when we produced this result, because it meant that the model was actually working very well. And so for the Carrington event, what we do see is that the electric fields are much, much larger than what we see in here. You can see just the base. These are on the same scale. And so you can see the base here is elevated than that. And so what came out of these studies then is that if we're going to have a Carrington kind of event, then we expect that the response of the magnetosphere-ionosphere system in terms of driving the electric fields on the ground would be twice what we have observed before in terms of the largest observations. And so for a Carrington event, there really needs to be concern. Now, the second thing that comes out of here is that typically, if you look at high latitudes, which is here, this is a depiction of the field aligned currents, region 1 inside and region 2 on the outer side, and various other current systems, is that when you have these extreme storms, you expect that the region which is influenced by these auroral currents can be pushed significantly from the high latitudes, and you can now see them in the mid-latitude, which comprises also the region where most of continental US falls. And so for some of the largest observed storms, we see it around 50 to 55 geomagnetic latitudes. But if we were to have a Carrington event, then the latitudes where we'll see these very large currents can suddenly be around 40 geomagnetic latitudes. And 40, just to put you in perspective, would mean the whole belt cutting across Washington, D.C., going upwards is included. And so all these power transmission networks that are on the same geographic or geomagnetic latitude as Washington, D.C., going upwards would be influenced by such kind of a storm. But remember, I said that we have also found that during these large storms, you also expect that there will be influence at the equator, and also there will be elevation in the mid-latitude itself. So such kinds of storms are really significant for us to understand the impact of, can be used in our understanding of the impact of space weather, extreme space weather, on the power operations of the power transmission grid. And so this is what we've been doing, and this is how significant this work is. If you're interested in something on extreme space weather, I have a poster on Wednesday, and you can pass by and we can talk about some of the extreme scenarios that we've been studying. And of course, the movement of this belt, where you have the extreme currents and the electric fields falling off, we established in a study that we did in 2003 that this is actually connected to the auroral current. And so what you see here is this is DMSP, Defense Meteorological Satellite Program, maximum energy flux data. And this is for all the 12 storms that we looked at between 1989 and 2005. And this supports the other studies where we established that this belt where the electric field falls off is actually varies between 50 and 40 geomagnetic latitudes. We're able to back that up by using energy observations from this DMSP satellite. Now, if you have been sleeping whilst I was talking, this is what you need to take away with you. Extreme space weather, and really the most important component that the power transmission operators are interested in, is the geoelectric fields, because this is what determines the level of GIC that is flowing on the power transmission line. And so, what we're doing in terms of our simulation, the extreme kind of event, is to understand the characteristics of the geoelectric fields when you model at very extreme level. This information is important for the power transmission networks. They will use this information to simulate what the influence would be on the grid by computing these GIC flows. And how this information benefits society is that they're able to do a sort of risk assessment for the power grid and understand which regions of the power grid is more susceptible to the influence of space weather. And then, depending on the outcome of these studies, they can then try and mitigate for those areas which are a concern on the whole power grid. So that's how significant the work on extreme space weather is in terms of the societal benefits. So in summary then, I'd say GICs are a major concern for the power transmission networks. And of course, because of the new federal regulation, all power transmission operators are now interested in getting information about the geoelectric field so that they can use it to model the effect or the impact on their transmission networks. And at the forefront of this transition is these magnetohydrodynamics models, which are helping us to push the research to the next level. And our research, of course, we're finding these extreme events that are important for establishing a worst kind of scenario that is then used for engineering analysis and mitigation of space weather effects on the transmission network. So with that, I say thank you very much, and I would like to acknowledge the following people. Dr. Antti Pukenin, who's here, for giving me an opportunity to come and work on this interesting topic. Of course, I love this work on GICs, and he's been very supportive since I came here. Also, just to acknowledge colleagues at CCMC and the Space Weather Lab at NASA Goddard Space Flight Center, of whom, without their help, this work would not be where it is now. And also acknowledge the various collaborators who have contributed in the work that I've been doing. And the University of Michigan, we thank them for making the space weather modeling framework publicly available. So if you're interested in using these models, you can just go to the CCMC website and you'll be able to use any of the models that I showed that you can use for your own studies. Of course, thanks to the AGU Award Committee for this award, which was established by Professor Schussler. And also I thank Dr. Judith Kapperman, who nominated me for this award. So thank you very much.
So thank you very much, Chigomizo. We will open the floor for questions, and there are mics on the alley, so please don't be shy and ask questions. Actually, I have one. So I was noticing that the event of 1859 was the biggest event. So from a naive perspective, what would happen if such event would appear right now? What would be the consequences?
Can we have the presentation back?
Oh, you can.
I can do that.
No, just speak to the mic.
Okay, all right. So what we believe can happen for an extreme Carrington kind of event, that's the Carrington event of 1859, is that if we were to have such kind of storm, then in terms of the geoelectric field, which is the most important parameter that is useful for the power transmission network, we would expect to see very high levels. And from our simulation, we anticipate that that could be about 2 times what has been observed from, just this one, yep. In terms of the maximum electric fields, the levels would be about twice what has been the maximum observed. So from observations, the maximum electric field is around 12 volts per kilometer. But if you go to a Carrington kind of event, then we expect the maximum electric fields we're able to get from our simulations were around 26 volts per kilometer. And so that is a very high level. And so it would be of very big concern for power transmission networks.
So
because
what kind of consequences?
The consequences is in terms of saturation of transformers. So some transformers may have the ability to sustain. Some transformers may not have a design capability that will enable them to sort of sustain such kind of current. And so what I personally believe is that we would have a large number of transformers going through half-cycle saturation effects. But as to how far this will go in terms of collapse of systems, that depends on individual system design and the equipment on the actual systems. So that is yet to be determined. So we're working with collaborators from the power industry who are using their models to try and see what could be the impact of such kind of electric fields on their systems.
So, are there questions? Yes, please.
Thank you. Very interesting talk. You talked about the new federal regulations and the power companies needing to understand how to mitigate this. So for mitigation, do you think it's mostly understanding when these GICs are going to happen, or is it a technology issue we have to build our power systems better?
From the regulation side, it's about building a power transmission network that will be sustainable. And so the power transmission networks, or operators rather, have to work at a standard which will enable them to, or will enable their networks, their systems, to sustain higher levels of current, the GICs. So that is what this regulation entails. They must do something to recognize that GICs are have a potential impact on their systems, and so institute some kind of measure to harden, sort of to say, their networks in preparation for the effects of GICs.
No more questions? Okay, so thank you very much again for a very interesting presentation. Congratulations for the prize.
Thank you.